Hello everyone, and I want to give a quick video here with an introduction as to why we're going to be talking about iterative solutions. I'm actually going to be talking today about why we're going to be doing iterative solutions. I'm going to actually be talking today about why we're doing iterative solutions. Sorry, that's a real bad joke, but anyways, iterative solutions, why do we care? Really briefly, all along your entire education has been based on the idea that we can solve analytically something explicit. So you have in algebra and calculus, we've always focused on problems that have a distinct and discrete solution, something that can be solved just as x is equal to some massive numbers or y is equal to some large function. And you should always solve it this way whenever you can. I mean, that's always the best plan, because if we can have an explicit solution, great. That's wonderful, because then we can get an explicit answer. We can get really nice trends and data. We can plot the things. It looks really beautiful. However, that's not always the case. Sometimes we deal with equations that are a little bit uglier, and sometimes we just want to know an answer. We just want to have the answer for a specific case, and we don't care if it's the most elegant solution possible, as long as it's the right one. So what are some examples? And I'll give you a quick example of this one. Is the classic one, just looking at things like the Ergun equation, which describes pressure drop in a packed column. And there's a lot of these kind of correlations and equations that exist, but this isn't a common one where you're looking at pressure drop, which is a change in pressure over length of column, and as a function of the size of particle packing, the size of things like the velocity of the system, and so forth. And also the porosity, just how much packing material is actually in there. And what you can see here is things like the pressure drop is going to behave linearly, right? There's a proportionality here, delta p, there's no inconvenience here. So if we knew everything else, we could analytically directly express p. We have a really nice linear expression that we can solve for and plot very nicely. However, things like the porosity in this equation, it's going to be fairly tricky to get actually a direct analytical solution. If you try to rearrange this expression to get delta p, you may run into some problems. Not that it's impossible, but it may not be worth your time to do that. Similarly, for things like the superficial velocity, the vapor flow rate, or in the packed column or liquid flow rate, this is also going to change, right? And that's also going to be nonlinear, because you have a term here and you have a term here that is going to make it more difficult. Again, they're quadratic based, so we might be able to get some solutions, but analytically. But in the long run, it may just not be worth it to us to try to solve this analytically when we just care about the final answer. And so an iterative approach, as I kind of alluded to in the beginning of this section, all forms one basic principle. You're going to guess a solution. It feels like you're bootstrapping yourself a little bit, but we have to make a guess. And then once we make a guess, we're going to refine and improve that guess until this answer solves us explicitly. And that's all the iterative approach does. Obviously, there are some concerns with this. You need to make a guess, and sometimes the guess has to be good. You have to be close to the vicinity of what the answer is to know what that is. And also, too, you only get one solution. You're not going to be able to plot, or I mean, you could, but it'd be very painful that if you want to try to plot over a wide range of numbers, that might not always be the easiest thing to do. And also, you might find that there may be several solutions to the problem, several routes, so to speak, and in which case you have to kind of guess and make multiple guesses to find each one of these routes. And finally, and probably the most painfully, is the convergence, or making a guess and then refining to the next guess, refining to the next guess. Ideally, the method you're using is going to lead you closer and closer and closer to your next correct answer, but it may not always do that. It may not always converge. And so you must always check to make sure that your answer is right. So these are kind of the limitations and the reason why we care about iterative approaches. But like I said, it's extremely common for us to use in engineering, and so it's important to know how to do it. And so we're going to, in the next series of videos, I'm going to go through these methods listed here. The first one is just simply plotting, using plots and graphically finding the solutions. Next is doing a direct substitution, or guessing and checking directly from the equation. doing numerical methods like Newton's equation, and then finally looking at optimization methods in Excel Solver or otherwise. So these are what we'll be talking about today or in these videos, and we'll start with the next one. Thank you.